Hey, I just wanted to quickly plug that if you guys want any tutoring, some new slots have opened. If you look in the description, there's a link to my physics and maths tutor profile in which I do tutoring on there. Hello, everybody. Welcome back to another episode of the A-Level Cookbook. Today, we're going to be doing the OCR A-Level Chemistry A, Paper 3 from June 2019. These short questions are from different areas of chemistry. Explain why a CF4 molecule has polar bonds but does not have an overall dipole. So number one, why has it got polar bonds? We have C and F, right? So F is more electronegative. That's why. Because if I just draw a diagram to the side, then C and F, if F's more electronegative, they're bonded covalently, so they have a shared pair of electrons. But if this is more electronegative, it will drag those shared pair of electrons towards itself, right? So it has got polar bonds because that's delta positive, that's delta negative, but it doesn't have an overall dipole. The reason it doesn't have an overall dipole is because C, F, 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 right? Like this. Imagine you're playing tug of war with your mates and you're all pulling in the same direction on this one guy in the middle who's sad, right? So it's like, help me, I'm being stretched. And you're all yanking this guy out, right? He's not going up, he's not going down, to the sides or anything. He's kind of in the middle, he's just getting stretched out. In a similar sense, that's kind of what's happening here. They're all kind of pulling the electrons towards themselves, all in the same amount, in the same direction. So because there's overall, symmetry, there's no dipole. So here, the effects cancel out because the pulling of the electrons this way is being cancelled out by that, and so forth. So that's why. So the reason is because there's no dipole because it's symmetrical. There. So it says, explain why a small proportion of molecules in water have a relative molecular mass of 20. You would expect it to be H2O, which is, 16, and, H2, so 2, so 18, right? But for some reason, 20. What's probably happened is that in order to have 20, it's got to be 16 and 4. Why would that be 4? You can't have H with an extra neutron in, right? And that's called deuterium. So what could happen is, you remember that we have lots of different isotopes just chilling all the time. So there may be different isotopes of hydrogen in this. So there's different isotopes of hydrogen in the H2O, such as 2H or deuterium, or tritium as well, which is 3H, anything like that. The idea is that there's different numbers of neutrons. The elements, the only things that can change here has to be the neutrons. It can't be protons because you've got a different element if you change the proton number, and it can't be electrons because the charge hasn't been changed either. There's no ionic exchange or anything like that going on. Now it says, what's the partial pressure of oxygen in a gas mixture containing this much oxygen by volume and a total pressure of this? So partial pressure equals mole fraction times the total pressure, right? If they've told you that there's 21% oxygen by volume, then that means that the mole fraction of this, mole fraction, remember, is the moles of the gas over total. If the total thing is this 21%, the mole fraction is also going to be the 21%, so 0.21. Because to work this out, you would just work out the mass of all of the mass of O2, or volume, of O2, really, all over the total volumes added up, which is just, volume and moles are proportional, so it would be moles and total in this. So that's mole fraction. So the partial pressure would just be 0.21 times the total, which is 1 times 10 to the 5, which gives you 2.1 times 10 to the 4. There you go. What mass of carbon dioxide is formed by the complete combustion of this much propane? So real quick, you've got to sketch out an equation because there's no way around it other than that. Because why wouldn't you do that, So here, we're burning C3H8, we're giving it O2, and we end up getting 3CO2, blah, blah, blah. I don't care the rest. All I know is that they're in a 1-to-3 ratio. That's all I care about. They've told you that we're combusting this much in propane at room temperature and pressure. So we can use moles of propane equals the volume over 24 decimeters cubed. But this is in meters cubed. So we're going to have to convert this. So it'd be volume over 24, but that's in decimeters cubed, that's in meters cubed, right? So you could go either way. You can either change that to meters cubed or this to decimeters cubed. I'm going to do it this way to convert into decimeters. So 1 meter is 10 decimeters. So then that means 1 meter squared has to be 100 decimeters squared because you're times it by 10, so you got to times it by 10 squared. So 1 meter cubed has to equal 1,000 decimeters cubed. So if I'm going from meters cubed to decimeters cubed, I'm going to have to do 42 times 1,000. If I do that, we get 1,750 moles. Now, we know it's moles. We know it's MR of CO2. So mass of CO2 would equal mole times the MR, which is going to be 1,750 times its MR, which is 44. But remember, this is the moles of propane, and they're in a 3-to-1 ratio. So we actually have to times that by 3 because it's one of the moles of the CO2. So it's going to be this times 3 times its MR, which if you do that, you end up getting 2.31 times 10 to the 8 grams there. So a reaction is first order with respect to H plus. At a pH of 1, the initial rate is this, and what's the initial rate at the pH of 3? So the rate is going to be proportional to the concentration of H plus. So when there's a pH of 1, they've told you that the rate was 2.4 times 10 to the minus 3. The H plus concentration would have equaled 10 to the minus 1. Now they've asked what is it when it's at 3. So at a pH of 3, H plus, well, what's happened to it? Well, now H plus has become 10 to the minus 3. So what have we done to get from here to here will happen to the rate. So what you could just do is you could do after divided by before, and I can tell you what you need to times the rate by. So after, it'd be 10 to the minus 3 divided by 10 to the minus 1, which is going to be 10 to the minus 2. Now would just be the previous one, so 2.4 times 10 to the minus 3 times 10 to the minus 2. If we do that, we get 2.4 times 10 to the minus 5. There you go. So now it says, what's the number of oxygen atoms in this many grams of that? So P2O5, if we were to split it magically into every single atom, you would have 2 P's and you would have 5 O's, right? So they're asking how many oxygen atoms are in this. Well, we can work out the moles of the P2O5, because that would just be its mass, 4.26 over its MR, 142. If we do that, we end up getting 0.03 moles. So if there's 0.03 moles of this whole thing, then for each one of them, there's going to be 5 times that. So the moles of O in each one of these is going to be 0.03 times 5, which is going to be 0.15. Then they want the number of oxygen atoms, right? And this is in moles. 1 mole is a quantity, like a dozen, for example. 1 dozen is 12. So if I have a dozen bananas, I have 12 donuts. 1 mole is Avogadro's constant as a number. So if I have 1 mole of bananas, I have 6.02 times 10 to the 23 bananas. So here, if I have 2 moles, I'll have 2 times Na. So if I have 0.15 moles, then it's going to be 0.15 times Na, Avogadro's constant, which gives you, so 0.15 times 6.02 times 10 to the 23, that gives you 9.03 times 10 to the 22. 9.03 times 10 to the 22. There. The reason that works is because, imagine this, I've got a box here with 3 spikes on it, 3 triangles. And I'm splitting it up into a box and 3 triangles. Right? If I have 1 box as a hunter, if I have the 1 unit, then there's 1 box and 3 triangles for every single one. So if I have 10 of these whole things, I will have 10 boxes of these and I'll have 30 of them. So it's the same principle here. That's why you can just split into these things. Each one of these numbers here is the moles of every single part. So benzoic acid is added to some foods as a preservative, and they prepare benzoic acid by mixing 4 centimeters cubed of phenyl methanol with that density and sodium carbonate, and then aqueous potassium manganate as an oxidizing agent. They heat it under reflux. They get this mixture. They cool it with acidified, and then they add, acidified concentrated HCl, and impure crystals of benzoic acid appear. They then recrystallize these to obtain 1.59 grams of pure benzoic acid. So here it says sodium carbonate makes the reaction mixture alkaline. Write an ionic equation to show how carbonate ions form an alkaline solution in water. So start by writing what you definitely know is in this equation. So CO3, 2 minus, and water. If something's alkaline, it's going to make water put out OH minuses. So then something else has to happen with the carbon, 8, the rest of it. So the C and the O's and the 2 of them. So it's going to make CO2 as well. Now we need to balance this because we have H2O here, right? So if we have H2O here, we're going to need 2 OH minuses here. Now we check it's all balanced. We've got 2 O's here, we've got 2 there. So that's 4 on this side. We've got 1 here and 3 here. That's 4 on that. Done. In step 2, explain why this mixture must be acidified so that crystals of benzoic acid appear. Right now, it's tempting to say that it would get rid of all of the hydroxide, but it's actually not that. The question's showing why would you get crystals of benzoic acid, right? Benzoic acid will have blah, 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 benzene chilling, right? But then benzoic acid would be COOH. If it's not appeared, then we don't have benzoic acid. It must be dissolved in whatever this whole thing here is. So what actually appeared here, before we acidified it, must have been COO minus. So for it to have become benzoic acid, it must have become COOH. That H must have come from somewhere, which is from the acid, because when you're adding acid, you're providing H pluses. That's the idea here. Because if it's alkaline, right, then that's going to dissociate into OO minus and give away an H plus. So if we add, so this is happy to be in its OH form, giving you benzoic acid appearing. That's the idea, and that's why it's hinting at making benzoic acid appear, which is OH, not O minus. So the reason is that this acid will provide H plus for C6H5COO minus to react with to form C6H5COOH, right? To form benzoic acid here. So you could kind of work backwards here and say, well, for some reason, adding acid makes benzoic acid appear. So let's take away acid, take away H+. So you kind of can work backwards like that as well. Write the overall equation for the preparation of benzoic acid from phenyl methanol. So again, write down just the basics first. So phenyl methanol is going to be C6H5 with a methanol on. So it's going to be CH, instead of CH3OH, it'd be CH2OH, right? And then we're going to add an oxidizing agent, and we're going to make benzoic acid, which has the formula C6H5COOH, right? Always write what you know first, then the rest of it you can fall into place like this. So what we do is, if you have a look, we have this OH here, but we've now got COOH. So for some reason, we've added an extra oxygen in, which is chilling. But at the same time, this COOH, H2 is gone. So we have to get rid of the H's somehow, and we've also added an oxidizing agent. So the other product you make is H2O. But the issue is now we haven't balanced the oxygens. We have one oxygen here, we've got two here, but an extra one there. So we have three here. So there's already one here. We need to add two more on, so you can add a two there. You can treat that like it's an oxygen, and that's how you balance it. Done. So now it says calculate the percentage yield of benzoic acid and give your answer to three significant figures. You need to always formulate some sort of equation so you know what you're dealing with, moles and stuff, right? Conveniently, right above, we've written one, and it's in a 1-to-1 ratio. Fine. We need to work out the percentage yield, which is going to be your actual like moles or mass divided by your theoretical moles times 100. Right? Let's see what in the question we have that we can use. So here, what have they done? They have mixed this much phenyl methanol with a density of that. Now that's a good clue, because if we have the volume and we have the density, 1 centimeter cubed has this mass, so this must have 4 times that. Density equals mass over volume. So now we can at least conclude that the mass of phenyl ethanol we'd used would have been 1.04 times 4. So I'm going to scribble that down somewhere. Mass of phenyl blah 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 would be 1.04 times 4, right? What else have we got from this question? So blah blah blah, they've done all of this. Eventually blah blah blah, they get this much benzoic acid. So we know the mass, or the actual mass of benzoic acid was, I've already forgotten it, well done ADHD, 1.59 grams. Cool. So you've got our actual mass. We're going to have to find our theoretical mass or moles. Either's fine. So if I know that the mass of the phenyl blah 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 blah, this stuff, phenyl methanol, right, was 1.04 times 4, which is 4.16 grams. I can work out the moles of this phenyl blah 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 blah, which would be 4.16 divided by its MR, which is 108. So then the moles of this phenyl, whatever, methyl, whatever, right, is going to be these two divided, which is going to equal 0.0385 moles. Therefore, the moles of the benzoic acid we would theoretically make should also be 0.0385. Therefore, the theoretical mass of the benzoic acid would be mass times MR, 0.0385 times the MR of benzoic acid, which is 122. If we do that, we get 4.697. So therefore, we have our theoretical, we had our actual wherever it's gone. So percentage yield would equal the actual, which was 1.59, divided by our theoretical, which is 4.697 times 100, which gives us 33.85. So we should do it to three significant figures, so 33.9. Done. So in step 3, describe how students can recrystallize these impure crystals to get pure benzoic acid. So the whole point of recrystallization is you're trying to separate aqueous, impurities from something that's insoluble in this sense. People started talking about using a drying agent. That's where you're separating two liquid things using their densities in a separating funnel and then drying them after. Here, we're not doing that. We're trying to separate out a solid product. So what you need to do is you first of all dissolve all of this stuff in the minimum amount of hot solvent. The idea is that you want to pick a solvent that your thing that you want is soluble in when it's hot. But when it cools down, it's no longer soluble in it, so it comes out and leaves all the other garbage in it. So then what you do is you would cool, then filter, wash with cold water, or cold, solvent in this case, sorry. And when you filter it, then you leave to dry as well. You don't add a drying agent to it. Because when you're cooling it, it's no longer going to be soluble in the solvent. It will just not dissolve. It will come out as a solid. You're filtering, you're getting rid of all of that extra solution that's stuck with it. And if you add some cold solvent to it, you can wash it as well. And If you leave it to dry as well, then obviously, none of that other stuff is in there and you've got a nice pure sample with all the other garbage out. Done. So this question's about groups and elements in group 14 or group 4 in the periodic table. There are 4 oxides of lead. A student carries out investigation to identify an unknown lead oxide, which is one of the 4 as shown above. They plan to reduce the unknown lead oxide by heating the lead oxide in a stream of methane gas, and the apparatus is shown below. So the student's method, let's see what's going on. So we've got methane gas coming in here, we're heating this, we've got a dish containing lead oxide, and we have a tube. Fine. What they're doing is they're weighing an empty dish, they add the lead oxides to the dish, and they reweigh, and they set up the apparatus past methane gas as shown, heat it for 10 minutes, pass cold air to cool the dish and the contents, weigh the dish and the contents. Fine. Bizarre experiment, can't lie. What are you doing with lead in a school, but whatever. Write the equations for the reduction of PbO2 with CH4. Right. So write down what you know first and we can talk about everything else. So Pb2O3 plus CH4. If something's being oxidized, something else has to be reduced. And if something's being reduced, something else has to be oxidized, right? So it's told you that this is being reduced. What in this is actually going to be reduced? It's probably going to be the lead. Lead here has got to have an oxidation state. Well, if this is O3, that's -6, that's got to be +6 overall, so it's got to be +3. So that means if we're reducing it, it's going to gain 3 electrons and form Pb, right? But when you're making it do that, something else has to then be oxidized in order for this to be reduced. So if we have a look here then, CH4, the oxidation state of carbon, is -4, that's +1. You could make CO2, right? And if you look at CO2, that's -4 +4. So can you see how this has gone from -4 to +4? That's been oxidized. So that could be something you'd make, right? So if we have that, we're going to make plus CO2. If we have a look, remember that these two each were +3 from what I said before. So we need 6 electrons overall to reduce these. But this goes from -4 to +4, right? So if you do 4 minus -4, can you see how this has lost 8 electrons, right? So we need to balance these. So from CH4 to CO2, we have lost 8 electrons, and the Pb2 to 2Pb has gained 6 electrons. So we need to find something that's, going to balance those number of electrons out. 6 times 4 is 24, 8 times 3 is 24. So we could have 4 of these, and then 3 of them. So then we end up with 4 Pb2O3, and then 3 CH4s. We're going to have 4 PBs here, but remember there's 4 PB2, so it's actually 8, and then 3 CO2s here. But we're not done because we have to check everything balances. So the PBs are balanced, the PBs are balanced, the carbons are balanced, the carbons are balanced, but we're stuck. We've not balanced the hydrogens or all of the oxygens. If you have a look, we only have 6 waters here, 3 times 2, right? But here we have 4 times 3, so 12. So we only accounted for 6 of them, so we need to make 6 H2O as well. And if you look, that's 12 H's, we've balanced out. There you go. You could do separate half equations if you wanted and recombine them, but you can do it like this as well. General rule of thumb is you always look at the number of electrons exchanging first, balance them based on the electrons, balance every other element that isn't H and O unless they are being oxidized or reduced. Then you balance O's by adding waters, and then finally you add the H pluses. Everyone likes to do it the other way around, where they do all the extra steps and then eventually put the electrons at the end. I don't think that's the best thing to do, to be honest, because you just kind of risk not actually having the right number of electrons transferred. So always do the electrons first. So this student uses safety glasses and a lab coat. State one other important safety precaution they should take when doing this experiment. So there's multiple things here. Look at what they're using. They're using methane gas. That's flammable immediately. That's very dangerous. As well as that, they're handling lead, which is toxic. It's straight up poisonous and can, you're going to have to wear gloves. And what else as well? Well, they're making some mysterious products that involve heating stuff. These compounds could have oxides of lead or gaseous stuff with lead in it, and CO2 as well, and all those things as well. Those could be poisonous. So any one of them, and the precaution, the poisonous one is using a fume cupboard. So I'm just going to say that lead is toxic, and then that's the reason we need to say what the precaution is. Wear gloves. Either any one of them is good, fine. So the student was not sure all of the oxygen had been removed from the lead oxide. Suggest 2 modifications that they could make to make sure that they could be confident all of it had been removed, and explain your reasoning. So there's practical elements to this and things they can do to this equation. So here, remember, look at the method. They're looking at weighing the dish of the contents. If they want to check it's all reacted, why not just keep weighing it until the contents are constant? Because what's happening is you're heating it, it's going to be losing some bits and bobs. You're making solid lead, so it's losing mass. So what you could do is just heat and reweigh until the mass is constant. Now, what else can we do to make sure all of the oxygen's gone? If you look at this equation, it's 4 Pb2O3 and methane. If I'm short on the amount of methane, that's not all going to react. But if I use loads and loads and loads and loads and loads of this, eventually every single bit of that possible is going to react. So what you could also do is just use excess methane as well to make sure all of it's gone. excess methane. There. Other things you could do is you could try and, for example, measure how much CO2 is made by bubbling it through lime water, and if, no more's being made, then it's done. But I think that's a bit meh, to be honest. I think those two are the strongest points. The student makes suitable modifications and then repeats them to get these accurate results. So here's the mass of the dish lead oxide and the lead at the end of the experiment. Work out the empirical formula of the lead oxide. Here, if we do this minus this, we can work out the mass of this lead oxide. If I do that, we get, so if I do 11.818 minus 8.364, we get a mass of lead oxide being 3.454. If we look between here and here, that mass must be the mass of O2 lost, which is going to be 11.818 minus 11.496. If we do that, we end up getting 0.322 grams. Fine. We now know that lead oxide and mass of O2 lost, so we can now work out the mass of lead. Because if this experiment's been done properly and perfectly, all the oxide is all the oxygen that's lost. So this minus this will tell us how much lead there is. So if I do 3.454 minus 0.322, we end up getting 3.312. 3.312. That's the mass of lead. That's the mass of lead oxide. They want the empirical formula of the lead oxide. So we now know what the PB, mass is and the O mass. We know that it's 3.312 grams and the O is going to be 0.322. So to work out an empirical formula, all you do is divide by the ARs and work out a ratio. So the AR of lead is 207.2 and then this is 16. If you divide those, you get 0.0151. And then you get 0.020125. Then you divide by the smallest number and you get a simplest whole number ratio, which eventually becomes PB3O4. Done. SiO2 and CO2 are oxides of other group 40 and 4 elements. Solid SiO2 melts here and solid CO2 melts here. Suggest the type of lattice structure in SiO2 and CO2 and explain the difference in melting points in terms of the forces when you're breaking them. So here we need to be careful. When we're melting and boiling, we are breaking bonds of some sort. So if we look at SiO2, it's tempting to be like it's macromolecular, but that just means big molecule. That doesn't necessarily tell you what the structure is. All right, the structure here is that it is a giant covalent lattice, because then it doesn't just say big molecule, it tells you that it's covalent, right? So what that means is that every single SiO2 is covalently bonded to every single other one. This is one of the few scenarios where actually boiling something is breaking covalent bonds, because every other time you don't get marked for that. Because the reason is imagine if I have I2 solid, right? And if I'm boiling I2 solid, I have I2 gas. That's because I'm not breaking the covalent bond here. What I'm actually doing is I'm separating them by breaking bonds between the molecules, intermolecular. But when the thing that you have is a giant covalent lattice, every single bond in it is covalent. And the same way with diamond and graphite. So when you're boiling and breaking, for example, diamond, you're breaking those covalent bonds. So in CO2, what's going on in CO2? Well, it is a simple molecular lattice, because the reason it's a lattice is simply just because it's solid. So now we need to explain why this has such a low melting point, whereas that has a really high one. It must be that whatever forces we're breaking here between the CO2s, which is going to be intermolecular London forces, are weaker than the bonds we're breaking here, which are actually the covalent bonds. So therefore, the reason is because CO2 has weaker London forces. That means it requires less energy to break compared to strong covalent bonds in SiO2. There you go. Dettol is a disinfectant containing this antiseptic, chloroxylenol, shown below. Chloroxylenol is a weak Bronsted Lowry acid. Anything that is an acid will put out an H+. It will lose an H+. Anything that is a base will react and gain an H+. Okay? Make sure you get that in your head. You can always say proton donor, proton acceptor, but you need to know what that actually means. So here it says, what is the systematic name of chloroxylenol? Right, so this is a bit tricky because we've got benzene, right? But we have an OH here. So the end is probably going to be phenol. All right, so it's phenol with a methyl, so dimethyl, and a chloro, right? 1, 2, 3, 4, 5. So it's going to be 4 chloro, because we always do it in alphabetical order. So C comes before D in dimethyl, right? 3, 5 dimethyl phenol. But it does allow 3, 5 dimethyl 4 chlorophenol. But that's what it is. Now it says predict the number of peaks in a carbon-13 NMR spectrum. The number of peaks is the number of carbon environments, right? So what you do is you've got to go and look at every single carbon bit by bit and see how many you can end up with. So this carbon is unique on its own, so there's 1. This carbon's different to this one, but they're the same on either side. So we have 2. That's a different environment. Here we have another carbon, which is identical to that. So that's our third environment. And here, that's our third. Here we have a fourth environment, which is different to all these others. So there's 4. And here we have a fifth carbon that's different to all these other ones. But it's the same as this. So we have 5 and 5. So the carbon environments in this would tell us the number of peaks, which is 5. Now it says, name the functional group responsible for the acidity of chloroxylenol and describe a simple test which could confirm the presence of this group. So here, the reason that it's an acid is that it's losing an H+. The only place where it can lose it from is the phenol group there. So the functional group is phenol. Now what we have to do is we need to try and test whether it's present. A simple test one is to look for whether there's a weak acid to begin with. So what you can do is you can use pH, like indicator paper or something like that. So you could use universal indicator, for example. I should have written universal, whoops. And that goes like orange / red maybe, or you could use a pH meter, but that doesn't prove phenol is there. All it's just saying is that it's weakly acidic. It could be a carboxylic acid group in this mysterious thing. So what you then do is you add a carbonate, like sodium carbonate, and it won't react. That then tells you, okay, yeah, this is a phenol. Right, that's the bit that's missing. So otherwise, you're just proving that there's a weak acid there. You're not proving that it's phenol there. And phenol does not react with a carbonate. So a student measures the pH of the contents in a bottle of Dettol. The label on the bottle shows that the percentage of chloroxylenol is 4.8%, as in 100 centimeters cubed of this will have 4.8 grams. Assume the following, that it's the only acidic component in Dettol. Chloroxylenol is a weak monobasic acid, and the density is that. Write the equation using molecular formulae for the acid dissociation of this, and then calculate the acid dissociation constant. Fine. Okay, so what we need to do is we can see here that's benzene with 2 methyl groups on it, and it's also got a Cl and an OH on it. So then if we just have a look, that's 1, 2, 3, 4, 5, 6, 7, 8. So we've got C8, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's going to be H9ClO, right? And it's saying, first of all, write the equation, so let's do that bit first. The acid dissociation of that is going to become, it's going to lose an H+, because acids always lose an H+, so C8HHClO- plus H+. There you go. I'm going to call this HA for the sake of my calculations. That's going to be A-, and that's going to be H+. To work out Ka, it's going to equal H plus A- over HA, right? Obviously, when I'm writing this, I'm going to write what Ka actually is, just so I get the mark for actually saying what the thing is, So it's going to be H+, and then C8H8ClO- all over C8H9Cl. Oh, cool. So if we want HKa to work this out, we need to work out a bunch of pieces of the puzzle. We need to find H+, A-, and HA. So if we have a look, what else have we got? So this person's got the pH of this. So immediately we've now figured out what H+ is, because H+ is just going to be 10 to the minus the pH, which was 5.14. We have one piece of the puzzle here. Fine. Now we need to figure out what HA is, or A-. So the acid concentration. Is there any way we can try and figure that one out? So if we have a look, chloroxylenol is the only acidic component. It's a weak monobasic acid, and it has a density of this. And they've also just told you that 100 centimeters cubed contains that much. So if we have a look there, if we have 100 centimeters cubed has 4.8 grams of this stuff, then why not change it to moles? So if I do 100 centimeters cubed, that would have 4.8 grams divided by the MR of this C8H9ClO, because that will tell me what it is in moles, right? So that's going to be 4.8 divided by its MR, which is 156.5, which is 0.03067 moles, right? So that means that every 100 centimeters cubed has this. Now, concentration is measured in moles per decimeter cubed. This is moles per 100 centimeters. 1 decimeter cubed is 1,000 centimeters cubed. So 1,000 centimeters cubed must have 0.3067. So therefore, the concentration is 0.03067 moles in a decimeter cubed. 1 mole, this whole thing means that 1 decimeter cubed has this many moles. I've just worked that out now. So it's going to be 0.3067. Fine. Now, A- is salt. There's no salt in this though, so we can't really do anything. Whenever you're doing a buffery question with KAHA and all that stuff, just a side note, HA is your acid, A- is the salt, not base, because base is OH- in this context of these equations. The reason it's not this is because, the salt is made from the base reacting with the acid. But the other thing as well is that we assume this is a salt because the dissociation constant's so far to the left that these two are practically the same. It's like 0.00001 and then 0.00002. Like making them the same is nearly, has no problem. So because this has only got weak acid and there's no mention of a salt in it, that must mean that Ka actually just equals H+ squared over HA instead, which would be 10 to the minus 5.14 all squared over the HA we just worked out, 0.3067. If we do that, we get 1.71 times 10 to the minus 10, and then we want the units as well. So it's mole per decimeter cubed square over mole per decimeter cubed, mole dm minus 3. There you go. Oh, actually, they've given it there. Whoops. Well, there you go. Decimal also contains other chemicals, including alpha terpineol. As shown in it's a chiral compound. Show where the chiral compound is. That's where you have 4 different groups around the carbon. Do it one by one. So no, you don't, because you have 3 H's. Here you got 4. You've only got 3 bonded things. Here you got 2 H's. Here you got 2 H's. Here you got 2 H's, because that's not benzene. Remember. Here we have an H, and this whole bit there, and this whole bit there, and then this whole bit there. That's different. So there's a chiral compound. This is the same as this. So that's not it. That's got 3 H's. That's got 3 H's, and that's got an OH and H and H and then this. So that's there where it is. There you go. So alpha terpineol meets the requirements for EZ isomerism, but only one EZ isomer exists. Explain why it can form EZ isomerism, and then whether it's an E or Z isomer and why only one exists. So let's do it bit by bit. So immediately one is that it has CC bond, like a double bond. Therefore, and, because it can't only just be CC bond. In order to have EZ isomerism, you've got to have 2 different groups on here and here. Otherwise, how are you going to put them on the same side if 2 of them are the same? So, and if you have a look here, each carbon atom has got like, this has got an H and then this whole bit, and this has got like, that whole bit and this CH3 there. So, and each carbon atom on the C-double-bond-C has, different groups on either side, right? Now we need to figure out which one it is. Is it E or Z? Here, there's a CH3, there's an H, and then there's all of this other stuff here and all of this other stuff here. These are higher priority than the CH3 and the H there. So therefore, this one has to be the Z isomer, because those higher priority bits with all those extra bits are on either, on the lower side. They're on the same side. So therefore, since both carbons' higher priority groups are on the same side, it must be, the Z isomer. Right? Cool. Now we need to explain why there's only one EZ isomer here. So if we tried to flip everything, then this would break off there and you wouldn't have a ring anymore. There you go. Or like you could say that the presence of the ring makes sure that these groups have to be on the same side. It's one of those things. You can't just say it's not impossible. You can't say it can't rotate, because that doesn't explain why this only has one EZ isomer. You can't rotate a double bond, which is why we have stereoisomerism in this context. So you can't just say it can't rotate, because that doesn't explain why this one can't. The only reason why is because the ring would just no longer exist. The ring would break if an E isomer formed. There you go. So alpha terpineol has 2 functional groups. For each one, choose a reagent that reacts with that group only and draw the structure of the products that you make. So if we have a look, the groups that we have here, we have an alkene and we have an OH. Right, so we have an alkene and an OH, which is stuck to a carbon with 3 of the carbons on. So it's a tertiary alcohol. And we have an alkene. So we need to think of a reagent that would react with this alkene that would not touch the other thing there. So one thing I could do is I could just add bromine water and it would decolorize, because it's going to react with this, but it won't touch that tertiary alcohol. There's nothing for it to do there. So there you go. There's one already. So what I could do is, well, there's I can add Br2, right? And the functional group that reacts is going to be an alkene group, or cycloalkene. And the product that you end up making is just going to be the same thing again. The double bond's just now single again with just bromines on it. So here. We're going to have this. We're going to have a Br there. We're going to have a Br here, like that. Drawn that so grossly. So it's there, and there. Done. Now, so because it's a tertiary alcohol, there's multiple things you can do that wouldn't touch an alkene. One thing you could do is you could just do some substitution. So you could swap this for like a Br using NaBr and H+, for example. So that's what I'm going to do. NaBr and like an H+ of some sort, and we're going to substitute. Because then you just have the same thing here, like this. The alkene's not touched because it won't react with this because it's nucleophilic, this mechanism, not electrophilic. And then you will have this, and then a Br here. Alternatives you could do is you could do a esterification, because that's an alcohol. It will you can make an ester with it. Also, you could do elimination and boot off, the OH, and then take it and the H2O as well to make an alkene there as well. But like any is fine. I'm going with that. There you go. On this question, then, you can see this is enthalpy changes, and it's a big fat question about reacting stuff together. Now, if you've seen any of my other videos, you know that I always say, read the dang question, know your enthalpy definitions, and you'll be smooth sailing. You may need to use a cycle, and even in the examiner report, a clear and logically response would include an energy cycle, as in a Hess's law cycle. So if you're not doing any of that, and you are complaining about knowing definitions and being like, why do I have to learn these, bro? Then you are doing all of this topic wrong and you are fumbling. So stop. Here actually makes sense of what's happening in this question. You can go and read the question and come back if you want, but just like use the text, please. If you have a look, it says calculate delta rate solution for CuSO4 solid for reaction 5.2 and then determine the enthalpy change of reaction for delta HR of 5.1. It says assume that the specific heat capacity of solution is the same for water. Show your working, including an energy cycle. Oh, would you look at that? It's telling you to do one. Whoa. So we have a look then. The enthalpy change of reaction, delta RH, is for converting anhydrous copper sulfate to hydrated copper 2 sulfate is difficult to measure directly by experiment. However, the enthalpy changes of solution of anhydrous and hydrated copper sulfate can be measured by experiment, and their reactions are shown below. So in experiment 1, they do an experiment to find the enthalpy of solution for reaction 5.2. What they do is they weigh all of this stuff together. They do this, they do that, they mix the two. I'm guessing, yeah, they mix it, they stir it, and then they get a temperature change. Wow. So all of this stuff then, this whole experiment is to look for the enthalpy of solution. In experiment 2, the student carries out a second experiment with this. The student uses the same method as experiment 1, and they get the enthalpy of solution to be this. So if you have a look at reaction 5.3, what did they do? They got CuSO4 with water of crystallization, and then they got the enthalpy of solution of the water of crystallization of this, and they ended up getting this value. So the best thing to do is collect all the information you know first before we dive into doing anything wild. Because what it's trying to do is work out the enthalpy of solution for this, and then eventually find the enthalpy of the reaction, enthalpy change of reaction. So if we have a look, let's do this first part where we actually look for the enthalpy of solution, right, for CuSO4 solid. Cool. So that's all of this reaction here. So what they've done is they've got the mass of this bottle plus the CuSO4 and the mass of the empty bottle, and then they get the mass of this final solution. So here we can work out the mass of the CuSO4 off the bat by doing that, subtracting stuff. So mass CuSO4 would equal this minus this, right? So the mass of that is going to be 28.04 minus 20.06, which is going to be 7.98 grams. So we know that we have 7.98 grams of the CuSO4. What about this polystyrene cup then? So it's the mass of solution, so we need that as well, which is going to be these two subtracted. So we're going to do 74.13 minus 23.43, which gives us 50.7 grams. Then we need to get the temperature change, delta T, which is going to be this minus this, which gives you 13.5 degrees C. Now the reason we've worked all of that out is because we can work out the energy change for this reaction. Q equals mc delta T, where Q is the energy change in joules, M is the mass of the thing having the energy change done to it, so either losing heat or gaining heat. C is the specific heat capacity of water, which is 4.18, and delta T is the temperature change. Right, so in this example then, Q is going to equal the mass of the solution, not the mass of the stuff here. So it's going to be 50.7 times 4.18 times the temperature change, 13.5, which gives us, so 2861.001 joules, right? But we want the enthalpy change of solution for this. That's not the enthalpy change of solution, because the enthalpy change of solution is, first of all, it's measured in kilojoules per mole, meaning 1 mole of this stuff causes the enthalpy change. And the enthalpy change of solution is where you dissolve 1 mole of a solid ionic compound in a blah, 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 whatever, right? 1 mole solid ionic compound. We don't know how many moles of the actual CuSO4 we used. All we know is that however much we did use gave you this. So we can convert that to kilojoules, no harm there. So that'll give you 2.861001, right? So I'm just going to round that to kilojoules. But we need to figure out how many moles led to that energy change. So the moles of CuSO4 is going to be 7.98 divided by its MR, which is 159.6, which gives you 0.05 moles. Therefore, 0.05 moles caused the change that was 2.861 kilojoules. We want to know how many 1 mole did. So if it's 0.05 moles did this, then 1 mole must have been, well, however many times we did to get up here, or divide this by itself, right? So then you would end up doing 2.861 divided by 0.05, which gives us 57.22 kilojoules per mole. However, this is gone up in temperature, so that's exothermic, right? So it's negative. So now we've worked out what the enthalpy of solution is for CuSO4 solid, which is going to be minus 57.22 kilojoules per mole. Cool, so we've at least got one part here done. Now we need to determine the enthalpy change of reaction for delta RH. So let's have a look at what that reaction actually is. The reaction here is showing you this. All right, so it's always helpful to write out the overall equation and see what we can do. So CuSO4 solid plus 5H2O liquid makes CuSO4.5H2O. CuSO4.5H2O. Every arrow in a Hess's law cycle is an enthalpy change, so you can write that there so you know that's delta HR, what we're looking for. Now, what else do we have in this question? Well, they've told you the enthalpy of solution of this thing is that, and we've just worked out the enthalpy of solution for CuSO4, right, solid, which we ended up getting was minus 57.22 kilojoules per mole, right? The enthalpy of solution is where you're dissolving 1 mole of a solid ionic compound, blah, blah, blah. So if you dissolved it, you would end up making aqueous ions, right? So what else do we have? Well, if you have a look, we have CuSO4 here. We've just worked out the enthalpy of solution of it. And we've also got the enthalpy of solution of this, where it's just solid delivery, whoops. So if you're doing the enthalpy of solution of both of those, you're going to make aqueous ions. So those will, become aqueous ions, all of their aqueous ions. So the arrow goes down from one solid to an aqueous ion, and solid to an aqueous ion. And you can't really enthalpy of solution water anyway, but you can write an arrow there if you want. So now we've just made a Hess's law cycle, because if we're going down here, we need to label that enthalpy change. That's minus 57.22. And here, this arrow, this person worked, that was what, 8.43? So plus 8.43. Hess's law says if you start and finish at the same place, the enthalpy change will equal the other root. So that means that the delta HR would equal, following this arrow, minus 57.22. And then we're going against this one, so minus 8.43, which is minus 65.65, which is roughly what, minus 65.7 kilojoules per mole. There you go. Making cycles is the only way to do all of this. If you don't do cycles, you are doomed. There is absolutely no other way to do it. No matter who's told you this, you can do that or this or that, what formula in this. Only way is by doing cycles. If you're not doing cycles, you're I don't know, man, you're smoking, I don't know what pack you're smoking. It even says in the examiner report, level 3 candidates use the master solution with MC delta T to get an energy change. They then found out to get they then divided by the moles of the CuSO4 to get the kilojoules per mole. And then they made a cycle. Oh my God. So yeah, the thermometer had an uncertainty reading of each temperature of this, and they calculated a 20% uncertainty. What was the temperature change? So percentage uncertainty is your uncertainty over your value, right? They told you it's 20 and times 100, sorry. So if I took the 100 out, then it would be 0.2. The percentage uncertainty as a decimal would equal the uncertainty. But remember, we did it with 2 readings, so it's going to be plus or minus 0.2, sorry. So 0.2 over their value, right? So then in order to work out their value, it would just be 0.2 divided by 0.2, which is 1. So they got 1 degree Celsius measured. That was it. The standard enthalpy change of reaction and the standard free energy change are here, and it wants it to work out the entropy change. So delta G equals delta H minus T delta S. Rearrange this first to get what you want so you know exactly what you're looking for, right? If I rearrange this, I'll get, if I move that to that side, T delta S would equal delta H minus delta G. So delta S would equal delta H minus delta G all over T. So we can start by working that bit out because they've told us what? They've told us. So now that we've got that, we have delta H, which is this. We have delta G, and they've told you it's the standard. So the temperature has to be 298 Kelvin. Cheeky, I know. If you didn't spot that that's the standard, then you were done for, which is very, very devious. Now, here then, delta S would equal delta H, so minus 55.8. So delta S would equal delta H, which is minus 55.8, and then it's minus what delta G is, which is minus 16.1. So can you see how there's a double? All over T, which is 298 Kelvin. So delta S would equal minus 0.13322, but be careful with the units because that's going to be in kilojoules per Kelvin per mole. So we need to work that in joules per Kelvin per mole because that's what the table's showing here. So it's going to be minus that times 1,000, sorry. So it's going to be minus 133.22. Right, joules per Kelvin per mole. Now, delta S equals the S end minus S start, right? If you have a look at this equation here, delta S would equal this end entropy, which would be this here, so 372.4 minus the entropy at the start, which is going to be, well, there's 5 H2Os, so minus 5 lots of 69.9 minus whatever this is, which we're going to call X, because that's what we're looking for, right? And we just worked out that this whole thing equals minus 133.22. So then 372.4 minus 5 lots of 69.9 minus X equals minus 133.22. So then what we do is we move the X to that side and then subtract that over. So then X would equal 372.4 minus 5, 69.9 plus 133.22. If I do that, we get plus 156.12, so roughly plus 156. You need to put the plus there because it's an entropy change. And it says 3 significant figures too. Cool. So now it says sodium thiosulfate contains a thiosulfate ion. The displayed formula is shown below. Predict the OSS bond angle. So when it's saying when it says the OSS bond angle, it's the one around the middle of the two things, right? So it's going to be between an O and an S. So it's the S. It's the angle here. And it says name the shape of the thiosulfate ion. So if you look around this bit here, the angle here, it depends on how many bonding pairs and lone pairs we have. You can treat double bonds as if it's a single one. So that means there's 1, 2, 3, 4 bonding pairs. There's no lone pairs. So that must mean that is 109.5 degrees and it is tetrahedral. There. In some of its reactions, the thiosulfate ion forms the tetrathionate ion, S4062-. The S4062- is a dimer of S2032-. Draw the displayed formula of the S4062- ion. I mean, if that's S-, and you can have another one of these next to each other, why not just join them together and share that extra electron that they have? So then it would be S, 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 O-, and then O-, and then double bond O, and then double bond O. Remember, that's got an extra electron. If you have another one with an extra electron, they can share that extra electron and form a covalent bond. Bang, like that. There you go. So this question's about the reactions of ion compounds. A student carries out reactions in this flowchart starting with iron 2 sulfide. So iron 2 sulfide, whatever, right? So it says in the box, write the formulas of A and B. So we have a pale green solution, we add Cl2 and we get an orange-brown solution, and then we add some NaOH and then we have an orange-brown precipitate. So if it's gone from pale green to orange-brown, to me that's saying that it's changed oxidation state. It is no longer 2+, it has become 3+ because of the colors. So it's an orange-brown precipitate and we add OH. It's going to be an Fe3+, but there's going to be OHs on it, so it's going to be FeOH3 solid. Generally speaking, when it's got in transition metal topics, when there's no overall charge again, because you replace it with OHs, you get a solid. Or like a liquid or a gas, depending on what it is, but here it's a solid. And we also should put the S there, sorry. Right, so if you have a look, we've got H2S, that's going to be S2-, we have AgNO3 here, right? If it's going to be a black precipitate B, it's going to be a solid something, and it's probably going to be something with silver in it. So it's going to be Ag something. It's probably going to be the S that it's reacting with here. And S is 2-, so it's going to be Ag2S, and it's a solid. And you can confirm that by then checking its mass on here, and it does add up to that. The student thinks that the reaction of iron 2 sulfide with H+ and H2O is a redox reaction. Explain with reasons whether they are correct. So if we have a look, where is that? H+ with H2O. Iron sulfide here to here. The question's quite funny. It's like, this student thinks this reaction is this, bro. Goofy ass. If we have a look, iron 2 sulfide is still Fe2+. The oxidation state is the same. So there's no change in oxidation state. The Fe is still +2. Therefore, they are incorrect. So it says, write the equation for the reaction of this with this. So start with what you know. So you know you're going to react FeH2O6 2+, and you're adding Cl2 gas. That's all. But then go look at the question, what we make in. So if we go back here, we now have an orange-brown solution. So that must mean that we still have the H2Os, and it's orange-brown instead, right? Because, so it's gone to an orange-brown solution, which to me tells me it's become Fe3+ on the other side. So the complex that we most likely have here, because the only one that would give you this color would be FeH2O6 3+. So then we need to figure out what's happened here. Well, if we have this, it's gone from 2+ to 3+, it's lost one electron. So if it's lost an electron, it's been oxidized, something else has to be reduced. So if that's reduced, we're going to end up with Cl- here on the other side, right? Now, we have 2 Cls here, so we have to have 2 Cl- here, so that means we have to, well, if you've got 2 of them taking an electron, we need 2 electrons to give, so there's got to be 2 here and a 2 here, like that. There you go. Construct an equation for the reaction of H2S gas with H+ and MnO4-. So again, start by writing what you definitely know is in this. You know you're going to react H2S, we're going to add MnO4-, and we're also going to be adding H+, and we need to figure out what we're making. So if you have a look back at this question, we have a colorless solution with Mn2+ and a yellow solid. So that means we must be making Mn2+ here, and the yellow solid is sulfur as a solid. So then we are also making the S here. Now we need to balance this by looking at what's happening in changes of oxidation. Always start by balancing the electrons, then the elements that aren't oxygen and hydrogen, unless they're being oxidized and reduced as well. Then you balance the oxygens by adding water, and then you finally add the protons. Everyone loves to do it the other way around, where they do absolutely every other step and then the hydrogens after. I think if you do that, you risk getting it wrong by missing out the amount of like electrons that should actually be exchanged. So number one is do the electrons first, I think. So what you do here, that's -8. Here, +7. So +7 -8. That's the oxidation state of this. So if that's +7, it's now gone down to, +2. It must have gained 5 electrons. Right? So scribble it down somewhere. The Mn has gained 5 electrons. Now, if that's the case, then something else must have lost electrons. Can you see how elemental sulfurs come from here and here? That must be -2. That must be 0, because that's +1, and there's 2 less of them, right? So then that means that S has lost 2 electrons. So to balance this, what we can do is times that by 2, times that by 5. So then we'll have 5 H2S's, 2 MnO4s, 2 Mn here means we're going to have 2 there, and we're going to have 5 S's here, right? Then we have to balance everything else out. So the Mn's are balanced, the S's are balanced, but we have O4, but there's 2 of them, so there's going to be O8, so we can add 8 H2Os on this side, right? And then if you have a look, the only thing left to balance is H+. So we have what? We have 8 H2s here, so that's 16. We have 1 here, and we've already got, well, how many of those? 10 used up there. So that means we're going to have to provide, well, in order to do 10 and however many of these, we need to have that to be 6. There you go. And that'll be 10 plus 6 gives you the 16 there. Done. So compound C is a hydrated ionic compound with this empirical formula, and the student investigates the thermal decomposition as outlined below. So what they do is they get 0.003 moles of this, and they heat it to remove the water of crystallization. 0.486 grams of water is collected, leaving this much of this anhydrous copper, this compound D. Then the student strongly heats this and decomposes it to form a solid oxide with a molar mass of that and a gas measured at room temperature with F and G. They then cool this gas mixture and they find that F is a compound that condenses to form 0.414 grams of a liquid. Gas G remains and it has a volume of this measured at room temperature, and it's tested and it relights a glowing splint. Figure out what C, D, E, F, and G are. Fine. So one thing we could do is work out how much water was lost, because I mean, if you've got, where's it gone? That much water collected, then we can figure out how much water was lost from there. So then that means the moles of H2O lost will be 0.486 over its MR, which is 18, which is 0.027 moles, right? They've told you here we had 0.03 moles of C, and it eventually, C.X-H2O, and then you eventually get X-H2O. So we were told that that's the 0. So we have 0.027 moles of this, and we've got C.X-H2O gives you this, so we can work out the ratio of the two, because we know that that's how many moles of that stuff we had, C. So 0.003 to this, divide by the smallest number, you'll get 1 to 9. So therefore, you know that it's going to be, the X in the H2O has got to be 9 H2O. Pretty sorted, fine. Now, if we have a look here, we know that compound C is a hydrated ionic compound with this empirical formula, fine. And we now know whatever this C is has to have XH2O, well, it's going to have 9 H2Os in it. So if we look at FeH18, N3O18, 9 H2Os would be, 18 H's, 9 O's. So if we take that, we're left with Fe, right, 3 N's, and then 9 O's. So we could figure out what it is, but we got to, we're looking like it's, possible what it could be, because it could just be NO3s. However, should probably try to go and calculate it back before sort of jumping back to that, So before we jump in and say, okay, that's definitely got to be NO3s, we need to go and see what else happens. So when they've got this compound D, which now just is FeN3O9, what they've done is they've, They heated it strongly to decompose and get a solid oxide E. They've told you that E, where is it? That's a solid oxide and it has that molar mass there. E is only just going to have Fe and O's in it, and it's got a mass of 159.6. I need to divvy this up to figure out, which combination of Fe and O gives you that MR there. So what you could just do is you could just add up multiples and see what happens. It's either going to be Fe2 plus or Fe3 plus, right? So that's either going to be FeO or it's Fe2O3. Work out the MR of both of them, and if we do that, the MR of Fe2O3 is that. So actually, we've now got what E is. E is going to be Fe2O3, right? So then, we need to figure out what on earth the gas F is and all of that other stuff there. Fine. Any other clues in this? Not really. So back to this other bit then, where I was saying we should probably be cautious. It's pretty all right to say we know that's got to be Fe3 plus. So working back up from the D thing that was D, it must be FeNO3 now, because we've got 3 N's, 3 N's, 9 O's, and it's 3 plus. So now let's just scribble that down. We know that D is going to be Fe NO3 and then 3, sorry. And then we know that C is that but hydrated, so it's going to be FeNO3 3.9H2O. The reason I didn't jump to saying it was NO3 before is I just wanted to double check that is 3 plus. Now we know that is Fe2O3. Now, once they've done that, we also get a gas mixture containing gases F and G, right? If we have a look here, from here to here, we've only lost we've lost the FEs, fine. We've lost a bunch of N's and O's as well. Now, if we write a quick balanced equation of this, FeNO3O9, right, there's going to have to be two of those to make 2Fe, 2O3. If you heat it, you're going to get Fe2O3. Now, if we have a look, the two Fe's are gone, but how many? We've got what? So 2 times 3, we've got 6 N's here, and we have 18 O's here. At the end of this, we have 6 N's left, and we have 15 O's left. So we need to figure out what's been made as well, right? Total volume of F and G is this, right? Now, they've told you that this F eventually condenses to give you 0.414 grams, fine. And G stays as a gas, but it relights a splint. So at least we now know that G has to be O2, right? We know that G is O2, and we also know that it has a volume now of 54 centimeters cubed. And this is at room temperature, so we can work out the moles of G by doing its volume over 24,000, which is going to be 54 divided by 24,000. If we do that, we get 2.25 times 10 to the minus 3 moles, right? The reason I've worked that out is because we'll have some number of moles of these, and these will eventually give you this gas volume in total, right? So because this is the total volume of these two gases mixed together, remember that you can just add up the volumes of all of these to get the total volume, and because they're ideal gases, we're modeling them as ideal gases, which means that the volume that F would have had, because these are both at room temperature, these just condenses after, the volume of F would have been 270 minus 54, which if we do that, we get 216, right? We can work out the moles of F by using its volume over 24,000 or 25 decimeters cubed by doing 216 over 24,000. If you do that, you get 0.009 moles. Now we know that it eventually becomes that liquid, and also it has this number of moles. So MR equals mass over moles, which would be 0.414 divided by 0.009. If you do that, you get 46. So then F has to be, well, we know that G is this. F has to be something that weighs 46 in its mass. So if it's got to be made of nitrogens and oxygen, so it's probably going to be, well, if NO is, if we do NO, that's 30. If I add another one, it's NO2, that's 46. So therefore, F has to be NO2. So what's missing? So we've got C, D, E, F, G, and that's it, actually. We've done it. There you go. Done. All right, thank you very much. Please like, share, and subscribe. You know the drill. And yeah, take it easy.